Good morning, everyone. Thanks for coming to this rescheduled seminar. It's supposed to be in the fall, but due to a number of things, we're doing it now. And it's also at the same time as one of the faculty, so there might be some people walking in a little bit late. So I apologize for the disturbance. But yeah, I am super pleased to welcome Dr. Bridget Deemer here to Lincoln to give a talk about some of her research on reservoirs. Bridget got her PhD at Washington State University, Vancouver, where she worked with John Harrison. She's currently a research ecologist with the USGS Southwest Biological Science Center in Flagstaff, Arizona, but is transitioning to also work with the Oregon Water Science Center. Bridget has been a Rail and Cole editorial fellow with the Association for Association of Advancing the Science of Limnology and Oceanography, ASLO, which runs the premier journal in limnological sciences. She's also been a PI and co-PI for over $3 million in grants. And her research on reservoir limnology is really synonymous with anyone that is talking about greenhouse gas emissions or methane, which she actually won't be talking about a ton today. We're talking about some of her new work, but I did just want to point out that Bridget's work is an amazing example of work that is not only important to advancing the science, but also relevant to society. Her work has been in the IPCC report, and she was quoted just this week in the New York Times on an article about using reservoirs for hydropower. So super excited to welcome Bridget today, and I will let her take her seminar.
Awesome. Thank you. It's been awesome to get to know some of you yesterday, and I really appreciate the invite from Dr. Corman, who I've gotten to work with on a couple of projects over the past 5 or 6 years now. So this photo is of Glen Canyon Dam, and it was taken when Lake Powell was a lot fuller than it is today. You can see the water backing up behind the dam. And we call the river below the dam the Glen Canyon Reach, which is just above Grand Canyon National Park. And that's where I've done a lot of my work over the past 6 years or so. Oh, right, and I have to point.
There we go.
Okay, so before I start digging into things, I just wanted to tell you a little bit about me. I've always loved being around the water. I grew up just down the street from a reservoir. The photo in the middle is me in undergraduate at Vassar College. I was fortunate enough to go for a few weeks over our winter break to Lake Tanganyika with my advisor, who was a biogeochemist. This was my first introduction to biogeochemistry. And it was also where my love of limnology started. And from there, I went on to do graduate work at Washington State, which has a lot of parallels to the University of Nebraska. It's another land grant institution. And I was also in a natural resource program there. This is a picture of me on a local reservoir. And the reservoir is called Lacamas Lake. I had no concept that it was a reservoir for probably the first summer field season that I was out there. And then I got out in the fall and the water had dropped 1.5 meters and the boat ramp was no longer accessible. And at that point, it occurred to me like, wow, this is actually a really different system than a natural lake. The water had gotten more turbid during the drop. And I started to get fascinated with this intersection between how we're managing this water on the landscape and what it means for the ecology and the chemistry of the water bodies, both the reservoir itself and also what that means for the downstream ecosystem. Okay, so from there, I entered a PhD program that was hosted by NSF. It was an interdisciplinary program that was aiming to link nitrogen biogeochemists with policymakers. Oh, whoops, it went forward. It's kind of like on a delay.
I can also sit there and just like
Advance it.
Yeah.
Yeah, that'd be awesome. So this is a picture of me in Washington, DC with some of the other members in the program. And they were really encouraging us to think about our nitrogen science and what we were learning and how we could kind of identify policy windows and communicate with policymakers some of the findings of our research or implications for decisions that they were actively considering and making. And as part of this, I got connected with folks at the Army Corps of Engineers and got funding to do a global review of greenhouse gas emissions from reservoirs. This was part of work that I had already started as part of my graduate program. And that sort of led to this integration of greenhouse gas emissions from reservoirs into the IPCC methodology, which was just a really cool opportunity for me to get linked in with that group. Right around that same time is when I met Dr. Corman at the Eco Days symposium. This is something that's funded by NSF and also I think some by ASLO, where early career scientists come together and they sort of brainstorm on topics of mutual interest. And so we got really interested in what are some of the fundamental differences between natural lakes and these more managed human constructed reservoir systems. And we were sort of thinking about this in a climate change lens. So how do reservoirs process energy and mass inputs differently than a natural lake? And one of the big things that came out of this for me was just this idea, which maybe is fairly obvious, but that management is a much more powerful control on what is exported downstream in a reservoir than a natural lake. And we can think about management in a number of different ways. It's not just management of the way that the dam is filling water on a single day. It's volumes throughout the year. It's also where that reservoir is placed on the landscape. And then there's also a lot of engineering features. I've heard about some of your reservoirs around here that have fountains below the dam. So it's, pretty variable in terms of what that can look like. It's really exciting when you start to think about the global distribution of these reservoirs and just how many there are and how many different types there are, to think about, there's a lot of opportunities for our science to inform a lot of these different management decisions that are taking place. So we estimate that there are over 1 million dams globally. This is from the Hydrosheds database on the top, just showing the distribution and the storage volume of dams globally. And then we also have a lot of hydropower projects in particular that are planned going into the future. So these hydropower projects are estimated to increase the production of global hydropower by over 70% over the next 25 years or so. And you'll notice, there's definitely hot spots for these projects. The United States is in a net decommissioning phase right now. So it's also really interesting to kind of think about the implications of that spatial distribution of these projects. So all that work just got me really excited about thinking about the intersection between management and reservoirs. And I landed with the US Geological Survey as the lead USGS scientist on a long-term water quality monitoring program at Lake Powell. And that program, it's funded directly through the Bureau. It began as part of the Salinity Control Act and actually concerns about salinity in the basin and agricultural activities and making sure that this reservoir wasn't just going to turn into a salt bin. But I work closely with an adaptive management program that thinks a lot about how the management of the dam is influencing the ecosystem below the Colorado River, below the dam. So today's talk, I'm gonna really focus on just talking about what it's like to work in an adaptive management program, and I'm going to tell you a little bit about the Glen Canyon Dam Adaptive Management Program. Then I'm going to talk about Lake Powell as a biogeochemical reactor and kind of how important it is in setting the stage for the ecosystem below the dam. And then I'm going to talk about some work that I've been doing recently to think about phosphorus cycling, controls on phosphorus cycling, and how phosphorus is changing with the drought, because phosphorus is really a key nutrient limiting the production both in the lake and below the dam. So the Glen Canyon Dam Adaptive Management Program was established in 1991 as part of the Grand Canyon Protection Act. And this was like a big deal because it was acknowledging that Lake Powell, even though it was constructed primarily for water storage and secondarily for hydropower, that it was really important to think about this dam also from an ecosystem perspective and from a recreational perspective. These types of decisions really set the framework for what dam operators are authorized to do in terms of their operations. So this process of setting up this program was basically giving a stamp, okay, we can be creative about how we think about managing this dam and start to think about other resources other than just the ones that the dam was originally constructed for. The Adaptive Management Work Group is made up of a variety of different stakeholders that all have different interests in the dam. And they come together and work with scientists to think about what are some of the resources that we want to manage for, how can we do that, what do we know about the science, about how things will respond to certain decision making about dam spill or storage in the dam, and what do we still need to learn. And so one thing that's really come out of this program is this broad acknowledgement by the scientists that the ecosystem is so altered that when we think about managing it, it's not really useful anymore to think about returning it or restoring it to a pre-dam state. We actually just need to think about where is the ecosystem now, and what are the resources that we identify as most important to manage for. That all said, I think it is really helpful to think about how much we have modified the hydrology. These two panels are showing historic baseline flows in, look at this for a minute, in purple on the top. And then the pink is the inflowing flow regime into Lake Powell. We have a seasonal scale on the top panel, and we have sub-daily stage fluctuations throughout a year on the bottom panel. And what you can see is that we really flattened the hydrograph. We don't have this big snow melt peak anymore. We don't have the low winter base flows that characterize this system. And we also have a lot more sub-daily flow fluctuation. And that just has to do with generating hydropower. So the dam releases water to match the demand for electricity, and that fluctuates within a day. So you get these tides of water that are like waves that move through the system and wet and dry the channel margins. And so I think that's a useful context. This panel was developed, we were asked to develop metrics of natural processes for the Bureau to think about how well are we mimicking natural processes in the river. This is one thing we came up with, but we also came up with this idea that it's more than just flow that's important. The dam's modifying flow, but it's also modifying the transport of sediment and carbon and nutrients. Historically, though, this program has really mainly focused on flow. It's a big lever at the dam. It's kind of what they have to work with in terms of thinking about changes to management. One thing the program experiments with are these high flow events, where for 24 to 76 hours or so, they'll spill out of the bypass tubes. This costs like upwards of $1 million in lost hydropower. So it's a big investment on the dam managers side of things, but it's an acknowledgement, we want to manage for these other resources. And the high flow events are designed to redistribute sand because this river is sediment starved. 95 to 99% of the sediment that comes into Lake Powell, it's staying there. And this river is, essentially just continuing to carve through the canyon. So we actually had one of these just last week, which was really exciting because it was timed kind of at a more natural time where we would expect snowmelt to start, whereas in the past, a lot of these high flow events have been in the fall. We also have been conducting what we call bug flows or macro-invertebrate production flows. And the idea with these is to promote egg laying of aquatic insects. So this photo is showing eggs being laid along the channel margin. And this process tends to happen around dusk. And in a river where you have a wave of water coming through from hydropower generation, there's a lot of spots in the canyon where when the eggs are laid at dusk, the water will continue to drop and the eggs will just dry out. So the citizen science project found that there were these hot spots of insect activity at parts in the canyon where the water was at its lowest at dusk. So the aquatic insects were laying their eggs right along the margin, and then for the rest of that wave, they remained submerged versus being desiccated, and insect production was better there. So they designed these flows, which hold the water low and steady over the weekend. And this was a collaborative experiment design with the folks that generate energy, with the idea being that there's less electricity demand on the weekends anyway. So this is, kind of a compromise, I suppose, between the interest in generating hydropower and the interest in providing this ecosystem service. So what we like to say is we gave the bugs the weekend off and gave them time to lay eggs that remained submerged with enough time for them to actually hatch. And sort of a side benefit of this experiment was that it also promoted higher rates of GPP in the river. And for a lot of rivers around here, you might think that's really not the best thing because they're already really enriched. And I know there's a lot of problems around here with harmful algal blooms and things. But this system I'm talking to you about today is a very different ecosystem that's nutrient starved. And so this, we think, has a positive benefit on the food web. And then finally, another recent flow that was conducted, we called the spring disturbance flow. This has only been conducted once, and it was sort of opportunistically taking advantage of the fact that the dam managers had to drop the water level low to do some repair on the area right below the dam. And so these low flows are not authorized in the law of the river and the way that the dam is normally operated. That's outside their normal operation. But it was a really exciting chance to think about, with ongoing drought and the possibility that we may be really only able to spill much lower flows of water into the future, what will the river look like under these low flows? So this is a picture with the dam in the background of just this really wide cobble bar that got exposed during these low flows. Okay, so that's kind of a broad overview of some of the flow experiments that the adaptive management program does. But like I mentioned in the beginning, dams aren't only altering flow, right? They're altering the transport of carbon and sediment and nutrients. And even though a lot of river ecologists and fishery folks tend to think about flow as a master variable, there's also a lot of other limiting factors that might control food webs in a tailwater ecosystem below a dam. And so I came into this adaptive management program as the first biogeochemist to be funded as part of the program. They had collaborated with Bob Hall and Emma Rosie Marshall and some other folks in the past to sort of appreciate that the biogeochemical perspective might be important. I came at a time when the fishery folks were starting to realize that flow might not be really the only thing that was controlling fish dynamics below the dam. And actually, yeah, that's fine to advance it.
Okay.
So dams are changing more than just the flow of water. We know that they retain a lot of nutrients. They're also estimated to produce 3 to 7% of all the anthropogenic methane emissions. They reduce sediment transport, and they also alter downstream thermal regimes. Okay, so I'm just going to talk about some of the biogeochemical effects that Lake Powell is having on the river channel. And I really like this video. This is just snapshots from Sentinel-2 images. It's not a perfect temporal representation, but it's showing you the Colorado River inlet to Lake Powell over time. And you can see how dynamic the location of sort of the transition zone between the reservoir and the river is. You can kind of, in some of these, even see like a plunge point where the turbid water is entering the reservoir. And that this river is carrying huge amounts of sediment. So it's depositing this sediment as it slows down and enters the lake. And then as the water levels fluctuate, that sediment's picked back up and moved. This cross section is showing, I believe this 0 mile is just like a point in space of where the reservoir starts, which we know is a really transitional area. But it's showing the pre-dam bathymetry in that region, so the elevation of the river channel. And then it's showing over these repeat surveys the accumulation of sediment in the inlet. And in some areas, this sedimentation is happening at a rate of 2 to 3 meters a year, which is like, you know, the height of the room we're standing in. It's an amazing amount of sediment. And it's contributed to the loss of 7% of the overall storage in Lake Powell. So it's a really big retention of mass. And one question I had when I first got there was, how does this retention of mass relate to salinity dynamics in the reservoir? Because the system, the whole Colorado River Basin has a lot of deposits that are old ocean deposits, really salty deposits to begin with. And then there's a lot of irrigated agriculture that's concentrating salt and increasing salinity inputs. And so we know the reservoir modulates salinity. The reservoir, an average drop of water that enters the reservoir is going to stay there for anywhere between 2 to 3 years. And so that sort of smooths out. So these purple dots are the salinity of inflowing water to Lake Powell, and the blue dots are the salinity of outflowing water. So we kind of smooth out the like sub-annual variations in salinity. And the effect that the reservoir has on downstream salinity is to is really to reduce these shorter term peaks in salinity. This dashed line is the salinity limit below Hoover Dam. And that's a salinity limit for irrigated agriculture. There's a lot of crops that will not grow well with water that's saltier than the 700 and something milligrams per liter TDS that's on this plot. Without the dam, Hoover Dam would be exceeding that. Without the 2 dams, that salinity limit would be exceeded like 40% of the time. So that's kind of an ecosystem service on its own. But then also was wondering, is the reservoir actually retaining salt with all that sediment that's being deposited? Is there any process that would retain some of the salt in the reservoir? And one important process that came to mind is this calcite precipitation. And this can happen across a variety of ecosystems. I actually feel like I was most aware of it because of Jess's work with calcite dynamics in Arizona streams. So I knew it was something that was happening local to the area. And in a reservoir, you sort of set up the perfect situation for this calcite precipitation to occur. Because the solubility of calcite is dependent on both temperature and pH. And you get more calcite precipitation with warmer temperatures, and you also get them with higher pH. So you have, when the reservoir, when the river enters the reservoir, you have this plunge point, which you can kind of see. I guess it's not coming out super well in this picture, but the turbid water enters, and when that momentum dissipates enough, it inserts itself in the lake in what's called a density current. And it's called a density current because its location in the lake is dependent on its density. And at that point, you have clearer surface water that's going to promote higher rates of primary production. The water is going to warm up, and then the pH is going to go up because of all that primary production, and you have sort of the perfect storm for precipitating calcite out of the ecosystem. So you're pushing towards this left side. Yeah. And so I did some mass balance work that I'm not going to talk through, but I am going to show you, this is data from the long-term water quality monitoring program. And this was another way to sort of think about what evidence we have for calcite precipitation. And what we can do is think about the ratio of calcium to magnesium. And if we consider magnesium relatively conservatively, any change in that ratio, any drop in calcium relative to magnesium is sort of a signature of potential calcite precipitation. And so what we did is look at that ratio, and the points are sort of color-coded for where they are in the reservoir. So especially in the San Juan arm, you can see you have much higher ratios of calcium to magnesium in the inflow, and then those ratios drop off as you move towards the dam. And the magnitude of this precipitation is pretty large. It's the rate of carbon deposition is about 2 times the average rate of CO2 emission from a reservoir globally. And the rate of calcite precipitation was higher than any other lake precipitation rate that's been reported in the literature. So this seems like a really important process in Lake Powell for both regulating alkalinity in the system and also potentially regulating phosphorus. So this overlays with phosphorus because phosphorus can bind on calcite. And we already knew before I entered the program, there had been a lot of work by Steve Glass that I'm not showing here, but also work by, I forget, Valerie Kelly, I think her name is, to look at ratios of nutrients entering the dam and then leaving the dam. And what both of those scientists observed is that phosphorus is retained in the reservoir at a much higher rate than nitrogen. So these are transport coefficients for water and then for specific nutrients. And the further you are below that line, the more nutrient is retained in the reservoir relative to water. So you can see that for orthophosphorus in the middle, the reservoir is retaining that a lot more than it is with nitrogen and silica. And that phosphorus retention has led to really severe phosphorus limitation, both in Lake Powell. Steve Glass did a lot of sort of bottle incubations and other nutrient limitation studies to show that the lake is phosphorus limited. And then below the dam, we have this incredible long-term record from the rainbow trout fishery. It's a lot easier to access the reach just below the dam than it is to study fish in the Grand Canyon just because it's a flat water system. So we have a long-term record that relates to phosphorus. And then we have sort of a shorter term record of an intermediary in the food web, this aquatic insect drift density. And the drift really tightly relates to the soluble reactive phosphorus concentration coming out the dam. And then the drift also positively relates to rainbow trout growth in that reach. And there have been a couple papers from collaborators kind of looking at these dynamics and relating a drop in phosphorus to a collapse in the rainbow trout fishery. Downstream, we have a lot less data on phosphorus concentrations because we're not capturing tributary inflows. We don't have a long-term phosphorus monitoring program there, but we do have estimates of primary production from oxygen sensors. And what we see is that native fish like the flannelmouth sucker are limited by primary production. Their growth rates depend on primary production in the river below the dam. And from everything we know, we expect that that directly relates back to this phosphorus supply issue. This is sort of consistent with global scale observations where reservoirs tend to retain more phosphorus than nitrogen, so do natural lakes. And thinking about how that imbalance affects the downstream ecosystem, I think is a really interesting question. This is sort of a nice case study of that stoichiometric shift. That said, I kind of already highlighted this before. This Lake Powell ecosystem is very different from a lot of other reservoir systems in that it's so nutrient limited. And we know, flying into Nebraska and looking at your reservoirs from the plane and just seeing all the agricultural across the landscape, we know that a lot of ecosystems kind of fall on the right side of these pictures, that they're culturally eutrophying from all the nutrient inputs from agricultural activities and sewage and other human activities. This idea of cultural oligotrophication was first put forward, as far as I know, in this paper by Stockner et al., where they talk about activities that actually reduce the transport of nutrients into aquatic ecosystems. And one of the key activities they talk about in that paper is the construction of dams. And this phenomenon has been studied quite well in British Columbia. Kootenay Lake is a really good example of an ecosystem that's extremely ultra oligotrophic, and they've actually conducted fertilization programs both in the lake and in the river below the dam to try to promote increased fish production in that ecosystem. But there's also examples in Sweden. There was a nice review by a collaborator of mine. I think is not published yet, but they're working on getting it published, that kind of summarizes all the ecosystems where fertilization experiments have happened. And they're predominantly British Columbia and Sweden, but there's examples kind of smattered all over. Okay, so now I'm going to talk a little bit about what we know about the controls on phosphorus in this ultra oligotrophic, or at least oligotrophic tailwater and in the reservoir. And then start to think about what kind of changes can we expect to see with this ongoing drought and with the declining water levels in Lake Powell. Okay, so I talked about all this calcite precipitation that's happening in the reservoir. And in addition to potentially sinking phosphorus, that also really changes the alkalinity of the ecosystem. So the ecosystem is less buffered to changes in pH. And you can kind of see that in the long-term record of pH from right below the dam. So these plots are at Lee's Ferry, which is just about 25 kilometers below the dam, and it's a long-term gauge site. We have pH data going back, I think, almost to 1950 in this plot. And you can see there's less variation in the period of record before the dam went in than there is after. And in some cases, you get these really anomalous dips in pH. And this dip is coincident with the really high phosphorus conditions that led to good recruitment of rainbow trout in Lee's Ferry, and then was followed by a collapse once the phosphorus dropped down again. So we kind of started to think about, maybe this calcite-bound phosphorus is really an issue in the tailwater and is really a dominant control. Whereas a lot of people tend to think of dissolved oxygen as a primary control in phosphorus cycling. And we do also have undersaturated concentrations of DO below the dam, because the dam is pulling water from the hypolympian of the reservoir or the metalympian of the reservoir. But they're not, they're not super low. The lowest in this sort of monthly average plot is about 6 milligrams per liter over the historic record. So this is a conceptual diagram that we came up with, just thinking about alternative hypotheses of what could be controlling phosphorus availability in these Colorado River sediments, and kind of asking, we think about in lakes, we tend to think about the sediment in the lakes as an internal source of phosphorus. But in rivers, really biogeochemists tend to think a lot more about watershed inputs and kind of think more of the river as a pipe in terms of phosphorus cycling. So we were wondering, could there be a store of phosphorus in the river sediments? And based on what we knew about all the calcite precipitation that was happening above the dam, maybe this is a factor below the dam as well. So when respiration happens, you drive down dissolved oxygen, but you also drive down pH. And so we designed some incubations to try to test, is this green pathway with pH more important than the dissolved oxygen pathway? And this is often hard to get at in an ecosystem, because oftentimes the low dissolved oxygen is coincident with the low pH, because they're both occurring in environments where there's a lot of respiration relative to photosynthesis. Okay, so in this plot here, this was the equilibrium equation that we had for calcite dissolution or precipitation. And now in red, I just added on this, this phenomenon I was talking about, where phosphorus can bind to calcite. So in red, you can have dissolved calcium and phosphorus on the low pH side of the equation, and then as pH goes up, it binds to calcite, and then that bound phosphorus, calcite phosphorus in the sediment is kind of sitting there waiting to be re-released when the conditions become low pH again. So we designed an experiment to test the controls on phosphorus bioavailability in the river below the dam, and to ask whether or not those sediments could be a big enough source of phosphorus to override the signature from the dam, because really right now the dam is the main source of phosphorus in terms of its contribution versus the tributaries below the dam. But we didn't know about the sediments. So we incubated sediment from 3 different sites, and I'll show you a map of where these sites are located. So Glen Canyon, I've already talked about. The Paria is a tributary that has some pretty big sediment inputs, and we were interested in understanding how sensitive those sediment inputs might be to pH fluctuation. And then Pierce Ferry is sort of the lower end of that Grand Canyon reach, right above Lake Mead, which is the next reservoir in the river ecosystem. I guess I better hurry up. Okay, so we treated these sediments at a variety of pHs. We also treated bottles that were oxygen free. And then we were able to measure pH and oxygen through these octodes, both in the sediment and in the water, kind of throughout the course of the incubation. And so what we expected to see is that as pH dropped, we expected calcium concentrations and phosphorus concentrations to go up as that calcite released from the sediment. Excuse me. And then we expected total protein production to also go up. So a signal of increased biological activity or alleviation of phosphorus limitation. And then we also conducted alkaline phosphatase incubations. Alkaline phosphatase is an enzyme that's released to try to cleave phosphorus from its binding sites and increase its availability. So we expected that that enzyme production would drop if phosphorus limitation was being alleviated by this calcite release. And across all three of the sites, we saw exactly what we expected with the total protein, where total protein production went up in the treatments that had low pH. And I'm not showing you the dissolved oxygen treatments, but there's no significant relationships with dissolved oxygen here. So that's pretty strong evidence that pH is an important control on phosphorus availability. And then in two of the sediments, we saw sort of a down regulation of the alkaline phosphatase production. We also saw increased calcium concentrations across the site, but the SRP signal was much lower in the tailwater than it was in the other two sites. And that sort of makes sense to us because a lot of the phosphorus that would normally reach that area right below the dam is held back in the reservoir. So we think what's happening is some really tight cycling where the phosphorus is sort of taken up as soon as it's released because the system is so phosphorus limited there. This change in phosphorus concentration with a 1 unit drop in pH from 8 to 7 is on the order of 31 to 39 kilograms of SRP per day across that reach from the Paria to Pierce, so that Grand Canyon reach. And if we do some extrapolations with production in Glen Canyon, that could lead to about 2 kilograms per day of increased insect production, which is a little hand wavy because this is the reach. I'm talking about the reach below the dam with this number. But the point being that this could be significant for food web production in the river. So water levels are dropping in Lake Powell, and we're all really interested in what that's going to mean for the food webs below the dam. We're thinking a lot about overall water availability and flow, but this declining water level also has really big implications for the water quality below the dam. So this is a cartoon that we made with a long-term data set from Lake Powell. And each of these time points is a summer quarterly trip that was taken in Lake Powell. So you're only looking at summer stratified conditions. You have warmer water on the top and the colder water below in the stratified reservoir. And samples are taken at each of these sites. And what you can see is that there's been a lot of fluctuation, and also that we're currently at the lowest that we've been since the reservoir started filling. So these temperatures that we're flashing over here are the temperatures of the release water. And we're currently just starting to actually enter the effluent median of the reservoir. So these are really unprecedented water quality conditions since the dam went in, although one could argue they're starting to kind of return to what they were before the dam went in, right, when the temperatures were a lot warmer. These water level declines also have consequence for dissolved oxygen dynamics in the reservoir. So I showed you earlier in the talk how there are these huge sediment deposits in the inflow. When we have a large spring inflow come in, it picks those sediments up and carries them in that density plume. And that carbon and nitrogen that's in the sediment promotes a lot of respiration. So these two cross sections are from this past fall and the fall of 2005, both of which were really low water level years. And you can see that this plume has hypoxic water in it. And I didn't show the penstop depth here, but in both cases, this resulted in low dissolved oxygen events below the dam that were a big concern for the fishery. This is a plot of the average middle and mean dissolved oxygen concentration from 2000 forward, plotted against minimum reservoir elevation for the year. So you can see as the reservoir is declining, those dissolved oxygen concentrations are dropping. We also did some general linear modeling that I'm not going to talk about, but it also shows this strong effective reservoir age. So as the reservoir gets older and more sediment is available to be picked up and moved, we're getting lower and lower dissolved oxygen. And that's reflected below the dam. This is historic water quality data from just below the dam. And the ribbons are the 10th and 90th confidence intervals of the historical record. And the black is last year. So you can see we're like 5 degrees warmer than historic temperatures. The dissolved oxygen dropped to about 3.5 milligrams per liter at one point. And the reservoir is turning over more now. So this higher conductivity water from the bottom got mixed up with the lower water levels. It took less energy to mix the lake. So big changes for the reservoir. And for phosphorus, also big changes in the pH regime. So as we start to draw water that's higher up in the reservoir, we're expecting higher pH water and less available phosphorus. The exception being those low dissolved oxygen events I just showed you are associated with low pH water. And so we're really interested to see kind of like how those things overlay to set the frame for phosphorus availability below the dam. The big outstanding question that I think we really need to test next is, you know, I talked a lot about pH today, but temperature affects that solubility as well. And so even if we have low pH in that metalimnian plume, if the water is a lot warmer, it may be that sort of inconsequential for increasing phosphorus availability, and then we continue to have a really depleted phosphorus signature below the dam. And so I'll just wrap up by saying that I think these water storage and release decisions are really important, not just from a water quantity perspective, which we're hearing about a lot in the news, but also from a water quality perspective and for thinking about the ecosystem below the dam and sort of the chemical signatures that are supporting that ecosystem. Water storage in Lake Powell is currently a really hot button issue. The BOR just released a draft supplemental EIS, and it's open for public comment until the end of the month. So if any of you want to make a comment on it, I would encourage you to do so. It's kind of a beast of a document, but it's a really interesting exercise to look at this and sort of engage with it. In that document, they're proposing different alternatives for how they're moving water. And one big decision I think that they're struggling with making is, are we really going to try to store water in both reservoirs anymore? Or are we going to prioritize one reservoir over the other? So I'm going to wrap up and just say I'm really excited about thinking about these questions, and I want to hear more about the reservoirs here in Nebraska and your questions. I did want to show this link, but I didn't get a chance to check and see if it worked. This article that Jess mentioned in the New York Times was an article about pump storage. And I'm really interested in thinking about this too, and just find it fascinating that, we're net decommissioning dams in the US, but we're also starting to get creative with thinking about different types of reservoirs and different ways of generating energy that might have sort of different implications for ecosystems. And this article has this really cool visualization that we may or may not get to work.
We may not get it to work.
Okay, well.
Let me work on that.
Okay. But you should go and check it out, and it's like a globe, and you can turn and see all the planned pump storage projects that are coming down the pipe, and it's pretty impressive. There's a lot of them in China. There's some of them in the US as well. And they're gonna, the idea is that they're gonna start to be a significant piece of the hydropower pie. And there's also a really cool data set that I haven't checked out that is available for any of us to download and kind of look at where are these systems. And think about what that means for the rivers in those areas. So with that, I'll take questions.
Really cool. I really like this kind of question as I think possession of phosphorus, tracking the phosphorus behind the reservoir. I would be interested to see how that compares to regions where calcium dynamics don't influence phosphorus, like in the plant. Because I can imagine really that's one of the values that was and no erosion and much more phosphorus.
Yeah, that's interesting. You're saying like in two systems that are like similarly eutrophic, the one that has more calcium and phosphorus will have less internal loading.
Phosphorus release.
Maybe, although a lot of times in those same systems that have low DO, the pH is dropping too, right? So it could be that you get phosphorus released from that low pH environment, similar to what you would with the iron bound phosphorus. But yeah, maybe not at the same rate, or maybe because it's colder. Yeah, it'd be interesting to compare those two scenarios and see. Oh, she got it up.
If there's,
Oh.
yeah, you can.
Let's see if we can. Yeah, so it just goes through and shows you the different regions of the globe and how much additional capacity. I don't know, maybe I just like flashy visuals, but I thought it was cool. Okay, I think that's it. Oh, here we go. Yeah.
I have a sort of a practical question. So we have a lot of reservoirs around here. And I think your ideas about, the multiple opportunities for reservoirs to be managed in different ways is really progressive. What do you think helps initiate those types of conversations? Because we obviously can't knock our door, knock on Corps of Engineers' door and say, hey, can we do this thing?
Yeah, that's a great question that came up at lunch with the graduate students yesterday. And I actually had a little slide here to, so I think, yeah, can you get over, so one really cool opportunity I had in grad school was actually to do kind of what you said and contact a local dam operator. And I think, it's about finding the right people in these positions, right? You have to make a connection within Army Corps that's interested in these questions like you are. Yeah, this is the slide. This was actually a dam operator at Pacific Corps. And I just emailed him to ask what the so a lot of these reservoirs have a rule curve that they follow. And they tend to just follow that rule curve perfectly to the T because there's no reason to do otherwise. But in reality, they have like a window of acceptable operation that they can work within. And that window is defined sort of by risk, right? Of like, what is the largest flood that might happen over a short period of time, where if you keep the reservoir too full, it's at the risk of, flooding over the top. But most reservoir operators will just keep with that sort of perfect rule curve and not really play around with their wiggle room. And we emailed to ask kind of what the rules were with this. This is one of the dams on the Klamath River, and it's a hydro peaking dam or a load following dam. So this is like its daily water level fluctuation signature. And normally they keep it perfectly, you know, the same height, same peak height and same minimum height every day. But we emailed to ask if there was flexibility because we wanted to know more about methane cycling in this reservoir. And we wanted to know if the methane that was being released was sort of in equilibrium with the sediment, and if there might be like a bigger pool that would be released when the water level drops. So methane, a lot of methane emission happens in the form of bubbles. So when you drop pressure, there's more bubbles to come up. And so they dropped the water further than normal in a couple of days. And instead of this sort of like relatively low rate under their normal operation, when they dropped it extra, we saw these big pulses in methane emission. And so it was like, it was just really cool, like opportunity for learning, where you can sort of design these like large scale experiments to learn something about your system. And the reservoir operator was just interested in, you know, understanding more about the system. He wanted to support the ecology, and it wasn't like really that much harder for him to do this. But I think it's the right person, right? It's finding, like sending emails and just asking questions about how the dams are managed. And some folks are going to be like too busy or not interested, but I think there are dam operators out there that are really interested in kind of optimizing the way they manage for the ecosystem and learning and interacting with ecologists. So yeah.
We have time for one more question.
Yeah.
Forget the exact number, but given that large percentage of hydropower dams are nearing or past their life expectancy, and that they alter the landscape, if we remove them, do you think there's some things that will never be able to return ecologically, despite removing some of those dams?
Yeah, that's a great question. And it's very like appropriate for this photo because this is one of the dams that they're removing. I think they're going to start prepping for it like within the year. I feel like that's you have as good a guess as I do. I mean, I find it fascinating. I think there's like a short-term transition period where things are going to be really different because there's just so much sediment behind these dams. I went out after the Elwha Dam was removed and visited it like a year after, and it's just amazing. All this, the river's just carving a new channel through these sediment banks. But I mean, I think there's positive stories in the Elwha of fish coming back, and
It's interesting you mentioned all the master's student who studied all the public commentary on that removal and some of the dynamics and the focus of some of those commentary. It was a social science. Fascinating commentary, and how it's turned out now is looking back at public commentary. It's fascinating with it, and what the situation is now, and with the tribes and stream and
Well, thanks, Bridget.
happening.
You had it.
Oh.
Today is the undergraduates lunch with Deemer. So if you did sign up for a Panera, they're right outside. Please sign your name. There's off the water right out.